Intermolecular forces. Hopefully you'll be able to hear me this time. I know the first video it didn't work very well. Um, Here, what we really want to start looking at is intra versus inter. This has already been highlighted because I tried this one time. It didn't work, you guys. But what we've been talking about so far is intramolecular forces that are forces within chemical bonds. And so we're talking about, like with water, it's the bond between oxygen and hydrogen. Now, excuse me, in this section, we're going to talk about intermolecular forces. So inter means between the molecules. So now we're talking about the bonds between one water molecule and another water molecule. Okay, so what happens when we break an intramolecular force? We have to have a chemical change. So if we want to make water, we have to break the bond between the two H's, we have to break the bond between the two O's, and then we have to form a new molecule. So bonds are broken within the molecule, and then new bonds are formed. So that's how intramolecular forces are broken. Now, intermolecular forces are a little bit different. Oops, sorry. So what we're doing is we're trying to separate two different molecules. Okay, so this is just a physical change. Okay, as you see right here, breaking glass, boiling water. And so what happens, I don't know why that keeps doing that, I'm sorry. What happens here is if you have more than one intermolecular force here, this is a dashed bond between the negative oxygen and the positive hydrogen here. So we would be breaking this bond. Or right here, this dashed line is between, again, the negative oxygen and the positive hydrogen. So when we're talking about intermolecular bonds, we're talking about breaking these bonds between the particles of water, one being here, the other one being there. Intramolecular would be the bonds here between, let me do that in a different color, between the hydrogen and the oxygen. So that's the difference. That's what we're talking about here. So one intermolecular force, I'll call these IMFs a lot, is a London dispersion force. So here we have to remember that all molecules have electrons. Electrons are going to move around. Okay, so what happens is they, for one little moment, they gang up on one side, and then they're lopsided, and they create a partial negative charge in one area and a partial positive charge in another. And we've talked about that already this chapter. And so this is what happens here. They end up all on one side, and so this side ends up partially negative, and then the other side where there's no electrons ends up partially positive. So that's how a London dispersion force works. It's kind of like static electricity when you pull all the electrons to one side. So this is a pretty weak force because it doesn't stay that way. Okay, partial separation of charges, it is temporary. That's really important to remember, and that's why it's very weak. So it's a very weak force that does not last very long. Okay, so it's weak. Here, right here again, it's the weakest of the intermolecular forces because the electrons just move back to where they started. Okay, so this is going to happen with nonpolar molecules. And again, it's temporarily polar for just a short amount of time. Then they move back, and so there's not always going to be a London dispersion force there. It's just every once in a while. Okay. I'm having a heck of a time here today. Sorry, guys. Again, so not permanent is a really important thing to remember. The strength, again, all molecules have electrons. So, gee, mini Christmas. All molecules have London dispersion forces. The larger the molecule, the stronger the forces. Okay, and that's just because they have more electrons. So the more electrons something has, the more strength it has. So just remember that all molecules are going to have LDFs. Okay, dipole forces, these are a little bit different here. They are permanent, and so it's because, again, of shifting of electrons, but it stays that way. So water is kind of an example of this, where we have one end that's always positive and one end that's always negative, and so we always have that charge there. So the strength here is a little stronger than the London dispersion forces because the attraction of the opposite charges is always there. Okay, that doesn't change. It's not temporary here, it's permanent. Hydrogen bonding then, what we have to remember is this is kind of unique because hydrogen only has one proton and one electron, and there's no other electrons there. So when the electron is shared unevenly, it just gets pulled further away from the hydrogen, and so the hydrogen becomes very, very positive. The three different molecules, we've talked a lot about this already, nitrogen, oxygen, and fluorine, are the ones that are going to cause this to happen. And it's considered a very, very strong dipole, okay, because there's no other electrons around. And so the hydrogen basically ends up acting like a proton or a very positive end. So the strength of a hydrogen bond, again, with no other electrons, to counteract that, we have a very positive end and a large positive charge with hydrogen bonding. And so this is the strongest of all the intermolecular forces. This kind of shows you what I tried to show you earlier here. This here is the attraction between the positive hydrogen and the negative. Here in this case would be negative electrons because and nitrogen is also very, very electronegative. Okay, so here we have nitrogen and hydrogen bonded together. So the nitrogen is pulling the electrons very close to itself, so this becomes very negative. The hydrogen is very positive. The weakest, again, remember here, dipole is going to be in the middle, LDF is the weakest, and hydrogen bond is the strongest. So that's the order of the strength for our intermolecular forces.